Okay, hello everybody. So last time we talked about the truth tables and we talked about formulas that are equivalent, that is formulas that have the same column of a truth table. So let me start by talking about some special kind of formula, special kind of sentences that have special truth table. So the first kind is a satisfiable formula. That's a formula where you have at least one line, at least one row in a truth table that evaluates to true. It's satisfiable because you could find a scenario that makes it happy, that makes it true. An opposite of satisfiable is an unsatisfiable formula, also called a contradiction. It's a formula which, no matter how you set the variables, no matter which scenario you pick, you cannot make it happy, you cannot make it true. And an example of such a formula is A and not A. Sometimes we even use A and not A to mean false, like a constant false. Finally, in addition to something that you could never make true, there is a formula that you could never make false, a tautology. You might have heard the expression of something being tautological, like if I say, if today is Monday, then today is Monday, it's tautological. Well, yes, it is a tautology because no matter if today is Monday or not, the sentence, if today is Monday, then today is Monday, will always be true. And there are more complicated sentences, like the one below, which also are true no matter how you set the variables A and B. So for a tautology, every line in the truth table will end with a true. So every entry in the last column will be true. For a contradiction, every entry will be false. And something is satisfiable if it's not a contradiction, essentially, if there is at least one line that's true. And oftentimes, given a formula, we need to know whether it's a contradiction or whether it's a tautology. If I give you a formula that describes, for example, a design of an airplane, and it consists of pieces that say, there is this scenario where things may go wrong, or there is another combination of factors that may lead to something not quite going right, and so on and so forth. You really want to look at this formula and say, you know what, I don't want any of those scenarios to materialize. I don't want any scenario where this formula would be true. But how long does it take? So we just saw the truth table, so we may say, oh, okay, let's just write a truth table. But even though computing just one line of the truth table is really fast, you plug in the values, you go up your tree, and you find out the answer. If you have n variables, you have to do this 2 to the n times, which grows pretty fast, pretty quick. And we are talking about airline design and hardware verification and stuff like that. You know, chances are you're going to talk about thousands and millions of different things that could affect whether the plane is flying, and the truth table becomes kind of longish. So just how long can it become? So would you really consider a problem solvable if it takes a really, really long time? Say it takes time 10 to the n, or does 10 to the n steps on an n symbol strings. So suppose you have a string of length 100, just 100. It's not that long. You could write things with more than 100 characters on a few lines. But if what you're doing with it takes 10 to the 100 times, even if you're doing billion steps per second, it will take 3 times 10 to the 32 centuries. If you're wondering how much it is, as far as I know, the age of our universe is projected to be way, way, way less. It's only 1.38 times 10 to the 10 years. And the number 3 times 10 to the 72, 3 times 10 to 72, that's comparable to the number of atoms in the observable universe. That's huge. You really don't want to wait that long. But you may say, wait a moment, but maybe we don't need to deal with strings of length 100. Maybe that's way too much. Maybe normally in life we only say formulas with 3 or 4 variables. Well, in this course, yes. But imagine that you're doing something in bioinformatics and you want to write a formula talking about the DNA. Well, DNA has 3.2 times 10 to the 9th base pair. And if you have a variable for every base pair, which, for example, will say whether this base pair is this or that, then you got yourself a formula with a huge number of variables. There are things where you wouldn't need the formulas that long, but that's because this is in the situations when we assume that dealing with the string is hard. For example, in cryptography, a key of 256-bit is considered more or less sufficient because we really don't know how to break those things faster. But going back to everyday big numbers, the number of Walmart transactions, the latest one I can find, which is fairly old, is 10 to the 9th. The URL searched by Google in 2012, that's when they actually told us how many URLs they searched, was 3 times 10 to the 12th. That's a pretty sizable number. You don't want to be doing an algorithm that runs in time 2 to this number, not any day soon. And even the number of Google searches per day is pretty substantial. It's 3.5 times 10 to the 9, which is almost the same number as the number of base pairs in the human DNA for comparison. So let's go back to our formulas and see how this relates. We ask, is it efficient to evaluate a formula with n variables? If you have a formula with 100 variables, like the formula describing specification for the aircraft, which would probably not even have 100, probably would have more like millions of variables, that would be already way too long and way too much. Can we do better? Can this course teach you to do better? Actually, that's a $1 million question. And I mean that it's a $1 million question. So here is what the question is. This question was formulated at the same time in Canada and in Russia, and they have slightly different names, with the Russian name being a little bit more descriptive because they have one word that translates as several words in English. So they have a word, peribor, which means exhaustive search. And they call this $1 million question the problem of exhaustive search. Is it possible to determine that a formula is a contradiction for every single formula without considering all the possible scenarios, all the possible assignments? Is it possible to avoid exhaustively going through every single scenario to find out the answer? Sometimes you can, but can you always? Other situations when no matter what, you cannot do better than really writing up the truth table. So in English, this problem is known as P versus NP. You might have heard about it. The name P versus NP comes from some historical reasons, and it's not words that you would probably know by this time. P stands for polynomial time computable, which is just a formal name of saying computable quickly. And NP really means efficiently checkable. And the question of P versus NP is is everything that's efficiently checkable also efficiently computable. So how does it relate to the exhaustive search problem? We know that in exhaustive search, we assume that looking at every potential solution, looking at every assignment is fast. But can we figure out something about the whole thing without looking at every specific assignment? That's the real question. Okay, why do I keep calling it $1 million question? For a very simple reason. If you solve it, you get $1 million. And what do I mean by the $1 million? Who's going to give it to you? The Clay Mathematical Institute, who in the year 2000 decided to take $7 million and to take 7 problems and assign $1 million for a solution to each of the problems. Most of the problems, I don't really understand what they're talking about. There's some deep problems in mathematics. But there is one problem which I just described to you and which you know what it means. That's the P versus NP problem. If it's easy to check that the solution to a problem is correct, is it also easy to solve the problem? That's it. That's all there is for this problem. If you solve it, you get $1 million. I would imagine there are probably easier way of getting $1 million. So there was one problem on this list that's already solved, and that's not the P versus P problem. Not for the lack of trying, because people who design aircraft, they really want to know how to check their specification fast. But so far, no such luck. So the reason I say that you already know what you need to do to solve this problem is a really cool thing called NP completeness, which essentially says that you could write any problem of the form, I have an efficient solution, I have a solution that I can check efficiently, as a formula. And moreover, such formula will be satisfiable when you have a correct solution. So you could disguise any problem of the form, I have a solution I can easily check, can I find it, as satisfiability problem. So the only thing you need to do to solve that P versus P problem and get the prize is to figure out if there is a way to check if formulas are satisfiable that always, and that's the caveat here, always works noticeably faster than truth tables. That's all. You have all the information you need to start solving it. Or you could show that it's impossible. Then people in aircraft design would not be as happy, but the cryptographers will be praising you, and you get an instant PhD and $1 million. So let me give you an analogy to describe you the problem a little bit more, and to describe you what you might need to do to solve it. So imagine that you have a bucket of apples. And maybe not a bucket, a crate, or something big. And you want to check whether there is a bad apple in the bucket. So think about a formula is a tautology. If all of its truth assignments are good, evaluate to true. It's sort of like saying, here is a huge bucket of apples, and I want to know whether all apples in the bucket are good. It's a very useful thing to be able to do, because if there is one bad apple, it can spoil the whole bucket. But you really don't want to take out every single apple and look at it. Can you do better? How about you smell the bucket? If there is something not quite right, chances are you might be able to tell it by the smell. So you can answer the question if all the apples are good or if there is a bad apple by smelling the bucket, avoiding the exhaustive search at looking at every single apple in the bucket separately. So here is a way to restate that $1 million problem. Can you find a smell test for satisfiability? Some way to look at a formula, do some magic over it that supposedly is less time consuming than writing the whole truth table, and say, yeah, this formula smells satisfiable, and this one smells like a contradiction. If you could do it, the $1 million is yours.